The act of human respiration is a complex mechanical and chemical process that serves as the primary interface between the internal biological environment and the external planetary atmosphere. During every inhalation, the lungs are flooded with a mixture of gases that is frequently characterized by the dominance of nitrogen and the vital necessity of oxygen. However, a precise quantitative analysis of this atmospheric fluid reveals a third, often overlooked constituent that enters the respiratory system in significant volumes. This substance is element 18, argon, a monatomic noble gas that occupies approximately 0.93% of the Earth's atmosphere by volume. To contextualize this concentration, there is nearly 30 times more argon in every breath than there is carbon dioxide, despite the latter receiving almost all the scientific and public attention regarding atmospheric composition. When these argon atoms enter the alveoli of the lungs, they do not participate in any metabolic exchange. They do not bind to hemoglobin, they do not catalyze enzymatic reactions, and they do not influence the pH of the blood. They enter and exit the human body in a state of absolute physiological indifference, functioning as a silent, invisible traveler in the biological stream. This lack of interaction is the defining characteristic of argon, an element whose very name is derived from the Greek word argos, meaning lazy or inactive. Yet this fundamental laziness has transformed it into the most critical, invisible guardian of modern technological and historical stability. The chemical nobility of argon is a direct consequence of its atomic structure, specifically the configuration of its electron shells. With 18 protons in its nucleus and a corresponding 18 electrons, argon possesses a completely filled valence shell, following the octet rule, with a configuration of 2, 8, and 8. This state of full electronic occupancy creates a condition of extreme thermodynamic stability, meaning the argon atom has no energetic incentive to share, lose, or gain electrons through bonding with other elements. While the oxygen in the air is aggressively seeking to oxidize surfaces, causing metals to rust, food to rot, and ancient parchments to disintegrate, argon remains a disinterested observer. It refuses to participate in the chaos of chemical reactions, and it is precisely this refusal that allows it to function as an ideal protective shield. This property of absolute inertness is utilized on a planetary scale to halt the progression of time for objects and materials that are most susceptible to environmental decay. Without the presence of this lazy gas, the fundamental infrastructure of global lighting would fail, and the most significant historical records of human civilization would have long ago surrendered to the corrosive power of the atmosphere. The preservation of high-value historical documents provides one of the most striking examples of argon's role as a guardian of human heritage. Within the National Archives of the United States, the original copies of the Constitution, the Bill of Rights, and the Declaration of Independence are stored in specialized, hermetically sealed encasements. For decades, these documents were kept under a helium atmosphere, but contemporary preservation science has shifted toward the use of high-purity argon. The choice is dictated by the physical properties of the gas. Argon atoms are significantly larger and heavier than those of helium, making the gas much less prone to leaking through microscopic seals or diffusing through glass and metal interfaces. By displacing all oxygen and moisture, the primary agents of parchment yellowing and ink fading, argon creates a molecular stasis field. In this environment, the oxidative processes that typically destroy organic fibers are physically impossible. The document is not merely stored, it is functionally removed from the timeline of chemical decay. This same principle is applied to the Magna Carta and other foundational manuscripts of global law, where argon acts as a permanent, invisible barrier against the entropy of the world. Beyond the preservation of the past, argon is a fundamental requirement for the illumination of the modern world. Within a standard incandescent light bulb, a tungsten filament is heated to temperatures exceeding 2,500 degrees Celsius to produce visible light through incandescence. At such extreme temperatures, if the filament were exposed to even trace amounts of oxygen, it would ignite and vaporize in a fraction of a second. Even in a vacuum, the tungsten atoms would rapidly sublime from the surface of the wire, causing the filament to thin and snap prematurely. To prevent this, engineers fill the bulb with a buffer gas, typically a mixture dominated by argon. The presence of argon atoms provides a physical pressure that pushes the sublimated tungsten atoms back onto the filament, significantly extending the lifespan of the lamp. Because argon is inert, it does not react with the white-hot tungsten, allowing the metal to glow for thousands of hours without structural failure. In this context, argon is the silent enabler of the artificial day, a material that allows for the safe containment of extreme thermal energy. The ubiquity of argon in the atmosphere is also a testament to its geological history, representing a breathing of the Earth's crust that has occurred over billions of years. While other gases like oxygen and nitrogen are recycled through biological and chemical cycles, argon accumulates as a permanent atmospheric fixture. Its abundance is not a result of primordial capture from the solar nebula, but of the slow radioactive decay of potassium-40 within the Earth's minerals. This process makes argon an essential tool for the scientific community, providing a mechanism for dating the very rocks that form the foundation of our world. The ability to measure the ratio of argon to potassium allows geologists to peer back through eons of time, mapping the movement of continents and the timing of ancient volcanic eruptions. This gas, which seems so passive and unimportant in the daily cycle of human life, is actually a high-resolution chronicle of the planet's internal evolution. The transition from a world of natural elements to a world of high technology requires a level of control over matter that is only possible through the intervention of the noble gases. In the realms of aerospace engineering, food preservation, and advanced metallurgy, argon is the primary instrument used to create __quote _6__, where the laws of standard atmospheric chemistry are suspended. It is a substance that demonstrates how stability and non-reactivity can be more powerful than aggressive chemical action. As we explore the multifaceted roles of element 18, it becomes clear that our survival and our progress are dependent on a gas that we cannot see, smell, or taste, and which refuses to acknowledge our existence. To ensure the continued production of high-density scientific narratives that reveal the hidden mechanisms of our world, the support of the audience is a critical component. Engaging with the content by subscribing to the channel, activating the notification bell, and contributing to the discussion in the comments section helps to sustain the reach of these educational explorations. Sharing your perspective on which atmospheric component you find most essential provides valuable feedback for the selection of future topics in this series of elemental investigations. The physical density of argon is another factor that dictates its utility in industrial applications. Being approximately 38% denser than air, argon can be used to __quote _7__ materials, settling into containers and displacing lighter, more reactive gases. This is the principle used in the protection of rare wines and sensitive chemical reagents. When a bottle of high-end wine is opened, the introduction of oxygen begins a process of oxidation that eventually turns the ethanol into acetic acid, spoiling the product. By injecting a layer of argon into the bottle, the heavier gas forms a protective cap on the surface of the liquid, preventing any oxygen from coming into contact with the wine. This invisible seal can preserve the flavor profile and chemical integrity of the liquid for weeks or even months. It is a sophisticated application of fluid dynamics and atomic inertness that serves both the culinary arts and the pharmaceutical industry. In the context of the global atmosphere, the volume of argon is staggering. Despite being considered a __quote _8__ gas, the total mass of argon in the Earth's atmosphere is estimated to be around 65 trillion tons. This mass contributes significantly to the total atmospheric pressure that we experience every day. Without the presence of argon, the physical characteristics of our atmosphere would be different, affecting everything from the boiling point of water to the flight dynamics of aircraft. We are literally walking through a massive, invisible weight that provides the structural backdrop for all terrestrial life. Argon is the silent majority of the minor gases, a constant presence that has been increasing in concentration since the solidification of the Earth's crust. It is a material that reminds us that the most significant influences on our environment are often the ones that are the most difficult to detect. The etymology of the noble gases often reflects their elusive nature, and argon is no exception. For nearly a century after the discovery of oxygen and nitrogen, the presence of argon went entirely unnoticed by the scientific community. It was a ghost in the machine of the air, a substance that was clearly present but which left no chemical signature for early chemists to find. The eventual discovery of argon in the late 19th century required a level of precision in measurement that pushed the boundaries of Victorian physics. This discovery did not just add another name to the periodic table, it revealed the existence of an entire family of elements that operate on a completely different set of rules from the rest of matter. It taught us that noble behavior, the refusal to react, is as fundamental to the universe as the aggressive bonding of carbon or the explosive reactivity of hydrogen. Argon's role in modern society is a testament to the power of the inert. We have built a world that relies on the rapid exchange of energy and information, yet none of it would be possible without the stabilizing influence of element 18. From the microchips in our computers, which are manufactured in argon-purged environments, to the double-paned windows that insulate our homes, argon is the invisible thread that holds our technological fabric together. It is a substance that demands no attention, yet its absence would result in a catastrophic loss of functionality in almost every sector of modern life. As we delve deeper into the origins and applications of this noble gas, we find a story that bridges the gap between the birth of stars and the preservation of our most sacred documents. Argon is the invisible guardian, the silent observer, and the non-reactive anchor of the human experience, and its story is only beginning to be understood in its full, cosmic and terrestrial complexity. The presence of argon within the planetary atmosphere is the result of two distinct and technologically significant narrative arcs, one occurring in the high-energy environments of distant stellar cores, and the other unfolding within the slow, radioactive silence of the Earth's deep crust. Within the broader cosmic context, argon is synthesized through a process known as the alpha process, which takes place during the advanced stages of nucleosynthesis in massive stars. When a star significantly more massive than the Sun nears the end of its life cycle, it undergoes a sequence of nuclear burning phases, transitioning from hydrogen and helium fusion to the fusion of heavier elements like carbon, neon, oxygen, and silicon. During the silicon burning phase, which occurs at temperatures exceeding 3 billion Kelvin, alpha particles, helium nuclei consisting of 2 protons and 2 neutrons, are captured by existing sulfur-32 atoms to form argon-36. Subsequent captures can produce argon-38 and eventually calcium-40. These isotopes, specifically argon-36 and argon-38, are the primary forms of argon found in the interstellar medium and the solar wind, representing the primordial argon that was present in the gas and dust cloud from which our solar system emerged. However, the isotopic composition of the argon found in the Earth's atmosphere presents a profound geochemical anomaly that differentiates our planet from the rest of the observable universe. In the solar atmosphere and the gaseous envelopes of the giant planets like Jupiter and Saturn, argon-36 is the dominant isotope. On Earth, however, argon-40 accounts for more than 99.6% of the total argon concentration. This overwhelming dominance of argon-40 is not a result of initial planetary accretion, but rather a consequence of the radioactive decay of potassium-40, an unstable isotope of potassium that is widely distributed throughout the Earth's silicate crust and mantle. Potassium is a fundamental component of many common rock-forming minerals, including feldspar and mica, and its radioactive isotope, potassium-40, has a half-life of approximately 1.25 billion years.
The decay of potassium-40 is a branching process. Approximately 89% of the atoms decay into calcium-40 through beta emission. But the remaining 11% undergo a process known as electron capture, where a proton in the nucleus absorbs an orbiting electron and transforms into a neutron, resulting in the creation of an atom of argon-40. This homegrown production of argon-40 represents a slow and relentless breathing of the Earth's geological foundation. Since the solidification of the Earth's crust over 4 billion years ago, potassium-40 has been functioning as a subterranean nuclear clock, steadily converting the solid matter of the crust into the noble gas of the atmosphere. Because argon is an inert gas, it is not incorporated into the crystal lattice of minerals during their initial formation from molten magma. Instead, it remains trapped within the mineral structure only as it is produced in situ by the decay of potassium.
As geological processes such as volcanism, tectonic subduction, and hydrothermal circulation cause the heating and melting of the crust and mantle, this sequestered argon is liberated and vented into the atmosphere. This process of planetary degassing has been occurring since the Hadean Eon, leading to the gradual accumulation of argon-40 in the air we breathe today. The 1% of the atmosphere that we identify as argon is, in a very literal sense, the accumulated exhaust of the Earth's internal radioactive furnace, a chemical record of the planet's deep-time geological activity. The significance of this isotopic accumulation extends far beyond atmospheric composition, as it provides the fundamental basis for one of the most powerful tools in the geosciences, Potassium-Argon (Kr) dating. This technique relies on the unique property of argon as a noble gas that is completely expelled from molten rock. When a volcanic eruption occurs and lava flows onto the surface, the extreme heat ensures that any pre-existing argon is released into the atmosphere, effectively, quote, 16 the radioactive clock to zero at the moment the rock solidifies. Once the rock cools and hardens, the potassium-40 trapped within the mineral matrix begins its slow decay into argon-40. Because the argon atoms are relatively large and chemically inert, they remain trapped within the crystalline structure of the minerals, accumulating over millions of years. By measuring the ratio of trapped argon-40 to the remaining potassium-40 in a sample of volcanic rock, scientists can calculate the exact time that has elapsed since the rock first solidified. This methodology has been instrumental in establishing the chronological framework for the history of life on Earth, particularly in the dating of hominid fossils in East Africa, where volcanic ash layers, known as tephra, bracket the sedimentary strata containing the remains of early human ancestors. The precision of argon-based dating was further refined with the development of argon-argon, 40Ar/39Ar dating, a technique that involves bombarding a mineral sample with neutrons in a nuclear reactor to convert stable potassium-39 into argon-39. This allows for the simultaneous measurement of both the parent and daughter isotopes through mass spectrometry of the argon gas alone, eliminating many of the uncertainties associated with traditional Kr dating. This advanced chronological tool has allowed researchers to date events with a precision of less than 1%, enabling the mapping of catastrophic volcanic eruptions, the timing of mass extinctions, and the rate of tectonic plate movement over hundreds of millions of years. Argon, the element that refuses to participate in chemical reactions, has thus become the primary narrator of the Earth's history, providing a mathematical anchor for our understanding of the deep time processes that have shaped the planetary surface. In the early stages of the solar system, the distribution of argon was also influenced by the process of atmospheric escape. While the Earth was able to retain much of its argon-40 due to its significant gravitational pull, smaller bodies like Mars and the Moon have experienced different atmospheric histories. On Mars, the atmosphere is thin and enriched in the heavier isotopes of argon, a result of billions of years of the lighter isotopes being preferentially stripped away by the solar wind. This isotopic _quote_17__ serves as a physical record of the Martian atmosphere's decline, proving that the planet once possessed a much denser gaseous envelope. On the Moon, trace amounts of argon-40 are continuously detected in the exosphere, originating from the radioactive decay of potassium within the lunar interior and being released through quote, 18 quote, and small-scale tectonic activity. This demonstrates that even on supposedly quote, 19 quote, worlds, the slow production of argon remains an active and measurable geological process. The total mass of argon in the Earth's atmosphere, approximately 65 trillion tons, represents a significant fraction of the total volatile budget of the planet. This accumulation has direct implications for our understanding of the Earth's thermal evolution.
Because the decay of potassium-40 is one of the three primary sources of internal radiogenic heat, alongside the decay of uranium and thorium. The amount of argon in the atmosphere is a proxy for the total amount of heat that has been generated within the planet since its formation. This heat is the engine that drives mantle convection, which in turn powers the movement of tectonic plates and the generation of the Earth's magnetic field. Argon is therefore not just a passive constituent of the air, it is the atmospheric byproduct of the very forces that maintain the Earth's habitability. The history of argon is the history of the Earth's energy, a narrative that connects the microscopic decay of a single isotope to the macroscopic movement of continents and the protection of the biosphere from cosmic radiation. Furthermore, the stability of argon isotopes allows them to be used as tracers in the study of atmospheric circulation and the exchange of gases between the ocean and the air. Because argon is not consumed by biological processes, its distribution in the deep oceans is governed entirely by physical processes, such as temperature-dependent solubility and the movement of thermohaline currents. By measuring argon concentrations in deep-sea water masses, oceanographers can determine how long it has been since that water was last in contact with the surface, providing critical data for models of global climate and the ocean's role in sequestering heat and carbon dioxide. Argon functions as an ideal tracer, a substance that moves through the world's systems without being altered by the messy complexities of biology or chemistry, providing a clear and objective view of the planet's physical dynamics. The cosmic scale of Argon's story also encompasses the search for life and the study of exoplanets. As astronomers begin to utilize advanced observatories like the James Webb Space Telescope to characterize the atmospheres of planets orbiting other stars, the detection of noble gases like argon will be a key indicator of a planet's geological maturity. A planet with a high concentration of argon-40 would suggest an active crust and the presence of significant amounts of potassium, indicating a geologically quote, 22 world capable of supporting the long-term cycles of carbon and water necessary for life. In this context, argon is a potential quote 23 or quote 24 by proxy, a material that points toward the complex internal mechanics that make a world suitable for habitation. The quote 25 gas of the Earth is thus a fundamental component of the universal language of planetary science, a substance that reveals the internal state of a world through its external atmospheric signature. From the perspective of quote 26 argon is one of the few materials that transcends the limitations of the biological era. While the oxygen and nitrogen in the atmosphere are constantly cycled through the bodies of living organisms and the chemical reactions of the surface, argon remains unchanged.
An atom of argon-40 that was vented from a volcano in the Archean eon, 3 billion years ago, is identical to an atom produced by a potassium decay yesterday. This lack of change is what makes it such a perfect witness.
It does not forget the conditions of its birth, and it does not adapt to its environment. It simply accumulates, filling the atmospheric reservoir and providing a stable, non-reactive backdrop to the chaotic history of life. The 0.93% of argon in the air is a permanent inventory of the Earth's radioactive heritage, a massive collection of atomic ghosts that have seen the rise and fall of every species that ever existed. The final consideration in the cosmic and geological narrative of argon is the concept of argon entrapment in the deep Earth. Recent high-pressure laboratory experiments suggest that under the extreme conditions found in the Earth's core, argon may not be entirely inert. At pressures exceeding 100 gigapascals, argon can theoretically form stable compounds with other elements, suggesting that a significant portion of the Earth's primordial argon, the argon-36 and argon-38 captured during accretion, may be sequestered deep within the iron core or the lowermost mantle. This would mean that the argon we see in the atmosphere is only a fraction of the total planetary budget, and that the deep Earth acts as a hidden reservoir for the noble gases. The study of argon at these extremes is pushing the boundaries of high-pressure physics, challenging our fundamental assumptions about the quote, _29 of the noble gases, and revealing a world where the most inert elements can be forced into chemical cooperation. As we look at the argon atoms circulating in the room, it is essential to recognize them as physical links to both the centers of massive stars and the deep history of our own planet. They are the survivors of kilonovae and supernovae, and the byproducts of the slow, cold nuclear fire that keeps the Earth's interior molten. They have been trapped in crystals for billions of years and have traveled through the atmosphere since the beginning of geological time. Argon is the silent chronicler of the Earth, the witness to the formation of the continents and the evolution of the atmosphere. It is the lazy element that does nothing but endure, and in its endurance, it provides the most accurate and uncompromising record of the world's existence. The following blocks will explore how this geological witness was discovered by human curiosity, and how its refusal to react has been harnessed to build the modern world, proving that, in the realm of the elements, the most passive players are often the most indispensable. The historical narrative of argon's discovery serves as a definitive case study in the power of scientific anomaly to dismantle established paradigms, proving that even the most well-studied substances can harbor fundamental secrets when subjected to the scrutiny of absolute precision. By the late 19th century, the scientific community operated under a pervasive sense of intellectual closure regarding the composition of the Earth's atmosphere.
The primary constituents, nitrogen, oxygen, carbon dioxide, and water vapor, had been identified and quantified with such apparent certainty that many prominent physicists believed the future of the field lay merely in the measurement of existing constants to a few more decimal places. However, in 1892, John William Strutt, the third Lord Rayleigh, initiated a series of experiments that would inadvertently expose a massive gap in the collective understanding of matter. Rayleigh's objective was seemingly mundane: to determine the precise density of nitrogen gas as part of a broader effort to verify Prout's hypothesis regarding atomic weights. He utilized two distinct methods for obtaining nitrogen samples. The first involved the chemical extraction of nitrogen from ammonia, while the second involved the removal of oxygen, carbon dioxide, and moisture from atmospheric air, leaving what was assumed to be pure nitrogen.
The resulting data presented a discrepancy that was statistically minute, yet physically profound. Rayleigh observed that the nitrogen derived from the atmosphere was consistently heavier than the nitrogen produced from chemical synthesis, with a density difference of approximately 1,000th, specifically 1.2572 grams per liter
for atmospheric nitrogen versus 1.2505 grams per litre for the chemical version. In the context of 19th century laboratory conditions, such a variation might have been dismissed as experimental error, but Rayleigh's reputation for obsessive accuracy and his rigorous elimination of variables made such a conclusion impossible. This 0.0067 gram discrepancy became the atomic ghost of the Victorian age, a signal that the atmosphere contained a hidden, heavy constituent that had remained undetected for over a century of chemical investigation. Rayleigh published his findings in a letter to the journal Nature, inviting the scientific community to offer a solution for the missing weight, effectively initiating a race to isolate the first of the noble gases. The challenge was accepted by William Ramsay, a professor of chemistry at University College London, whose approach was defined by aggressive chemical intervention. Ramsay reasoned that if atmospheric nitrogen contained a heavier impurity, that impurity must be chemically unreactive, allowing it to survive the various processes used to extract the other gases. To prove this, Ramsay utilized a technique of high-temperature sequestration, passing atmospheric nitrogen repeatedly over red-hot magnesium ribbons. Magnesium possesses a rare ability to react with nitrogen, forming solid magnesium nitride. By continuously circulating the gas over the heated metal, Ramsay was able to chemically scrub the nitrogen from the sample. As the volume of the gas decreased, the remaining fraction became increasingly dense. Eventually, Ramsay was left with a small, persistent bubble of gas that refused to react with any substance, regardless of the temperature or the severity of the chemical treatment. This was the moment of isolation for element 18, a substance that had been inhaled by every human being in history, yet which had never once been identified because of its refusal to participate in the chemical world. The characterization of this new gas presented an immediate crisis for the prevailing models of atomic structure. When Rayleigh and Ramsay subjected the isolated gas to spectroscopic analysis, they observed a unique pattern of light, distinctive red and blue lines that matched no known element in the solar or terrestrial catalogues. Furthermore, measurements of the gas's specific heat ratio, the relationship between its heat capacity at constant pressure and constant volume, yielded a value of 1.67. According to the laws of thermodynamics, this value was only possible for a monatomic gas, meaning the substance consisted of individual unbonded atoms. This was a radical departure from the behavior of all other known gaseous elements like hydrogen, nitrogen, and oxygen, which exist as diatomic pairs. The researchers proposed the name __34__, derived from the Greek word for underscore, _35__, to reflect the gas's total lack of chemical affinity. However, the announcement of argon's discovery in 1894 was met with profound skepticism from the scientific establishment, including the architect of the periodic table himself, Dmitry Mendeleev. The problem lay in the fact that there was no logical position for argon within the existing periodic table. Based on its measured atomic weight of approximately 40, argon should have been situated between potassium and calcium, but its properties were entirely inconsistent with those highly reactive metals. Mendeleev initially argued that argon was not a new element at all, but rather a condensed form of nitrogen, _36__ molecule similar to ozone, N3N3. The debate was not merely academic, it threatened the structural integrity of the periodic law, suggesting that the table was either incomplete or fundamentally flawed. The resolution of this crisis required the discovery of an entire family of previously unknown elements. Over the subsequent 4 years, Ramsay and his assistant Maurice Travers utilized the newly developed technology of liquid air distillation to isolate helium, neon, krypton, and xenon. This series of discoveries revealed the existence of an entire 37, now known as the noble gases,
situated at the far right of the periodic table. These elements provided the __38__ in the structure of the atom, eventually leading to the realization that the chemical behavior of elements is dictated by the occupancy of their electron shells. The discovery of argon also represented a historical vindication of the work of Henry Cavendish, who in 1785 had performed a remarkably similar experiment nearly 110 years earlier. Cavendish had utilized an electric spark to force atmospheric nitrogen to react with oxygen, forming nitrogen oxides that could be dissolved in an alkaline solution. After days of continuous sparking and the removal of all detectable gases, Cavendish noted that a tiny bubble, about 1/120th of the original volume, remained stubbornly unreacted. Lacking the spectroscopic tools and the vacuum technology of the late 19th century, Cavendish could not identify the nature of this __39___. Yet his meticulous records allowed Rayleigh and Ramsay to recognize that they had finally isolated the substance that Cavendish had first glimpsed in the 18th century.
This continuity of observation highlights the incremental nature of scientific progress, where the anomalies of one era become the breakthroughs of the next. The impact of argon's discovery on the trajectory of modern physics and chemistry cannot be overstated. In 1904, the dual recognition of the isolation of the noble gases resulted in a rare simultaneous awarding of Nobel Prizes. Lord Rayleigh received the Nobel Prize in Physics for his density measurements and the discovery of argon, while William Ramsay received the Nobel Prize in Chemistry for his discovery of the entire group of noble gases. These awards signaled the final acceptance of the monatomic inert elements as a fundamental component of the universe. The discovery of argon proved that __40__, the lack of chemical reaction, is a physical property as significant as the most violent reactivity. It forced a total re-evaluation of valence, atomic structure, and the nature of the chemical bond, providing the empirical foundation for the development of the octet rule and the Bohr model of the atom. The __41__ of argon's history is found in the way it challenged the limits of human perception. For centuries, the air was considered a simple, life-giving fluid, yet hidden within that fluid was a trillion-ton reservoir of a gas that was chemically invisible. The story of its discovery is a reminder that the most significant components of our reality are often the ones that do not demand our attention. Argon does not explode, it does not sustain fire, and it does not allow us to breathe. It simply exists in a state of absolute, noble stability. This historical aspect of the element reveals that our understanding of the world is often a matter of sensitivity to the smallest discrepancies. The 0.0067 gram difference in density was the thread that, when pulled, unraveled the secrets of the noble gases and provided a more accurate map of the building blocks of the universe.
The historical transition of argon from a __42__ to a __43__ also mirrors the industrial evolution of the 20th century. Once its properties were understood, the gas was immediately recruited for service in the very labs and factories where it had been discovered. The isolation of argon made possible the development of vacuum technology, the production of high-purity metals, and the advancement of welding techniques that allowed for the construction of modern cities. It moved from being a theoretical problem to being a practical solution, demonstrating that fundamental scientific inquiry often produces the most essential industrial tools. The story of argon is thus a narrative of human intelligence expanding into the voids of the natural world, identifying the __44__ of the atmosphere, and utilizing their properties to stabilize the progress of civilization. Reflecting on the drama of the late 1890s, one can see the discovery of argon as the closing act of classical chemistry
and the opening scene of the atomic age. It was the last great mystery of the air, and its resolution provided the blueprint for the modern periodic table. The gas that Rayleigh and Ramsay found in their London laboratory is the same gas that currently protects our light bulbs and preserves our history, a substance whose refusal to react has made it the most reliable witness to the development of our scientific understanding. Argon's journey through history is a testament to the fact that in the realm of the elements, the quote, 45, and the quote, 46, are often the most profound agents of knowledge. It stands as a silent sentinel of the atmosphere, its discovery a reminder that the universe is always more complex than our current models suggest, and that a single % of the air can hold the key to the structure of all matter. Furthermore, the discovery process established the standard for modern isotopic and spectroscopic analysis, which remains the primary method for identifying new materials today. The collaboration between a physicist obsessed with density and a chemist obsessed with reactivity created a multidisciplinary approach that would define the next century of scientific endeavor. They proved that the air is not just a medium for life, but a complex museum of the Earth's geological and cosmic history, with argon serving as the most stable and permanent of its exhibits. The 0.93% of argon in the air is the legacy of this historical drama, a physical reminder of the moment when humanity finally recognized the presence of the quote, 47, elements. The following block will explore how this quote, 48, was put to work in the hidden machinery of our daily lives,
transforming from a laboratory curiosity into the invisible shield of the modern technological world. The transition of argon from a 19th century laboratory anomaly to a cornerstone of modern industrial utility is a direct result of its thermodynamic stability and its specific physical constants, such as thermal conductivity and atomic mass. In the contemporary technological landscape, argon functions as the primary quote, 49, a material used to create an environment where the aggressive chemical reactions typical of an oxygen-rich atmosphere are physically suppressed. This application is most critically observed in the field of advanced metallurgy, specifically in the process of gas tungsten arc welding, GTAW, commonly referred to as TIG, tungsten inert gas welding.
When joining reactive metals such as titanium, aluminium, or high alloy steels, the presence of even trace amounts of oxygen, nitrogen, or water vapor at the high temperatures of the welding arc, which can exceed 6,000 degrees Celsius, would result in immediate oxidation and the formation of brittle inclusions, rendering the joint structurally unsound. To prevent this, a stream of high-purity argon is directed through the welding torch, creating a localized, high-pressure quote, 50 that completely displaces the surrounding air. Because argon is 38% denser than the ambient atmosphere, it effectively quote, 51 quote, the molten weld pool, serving as a non-reactive barrier that allows the metal to solidify in its pure state. This quote, 52 of the gas is the only reason for the structural integrity of modern jet engines, spacecraft hulls, and deep-sea submersibles, which rely on the flawless fusion of reactive alloys. The role of argon as a thermal and chemical stabilizer is equally indispensable in the history and continued operation of the lighting industry. While the previous narrative established the discovery of argon in the context of Victorian physics, its practical application solved the quote, 53 of early incandescent lamps. In a vacuum-sealed bulb, the tungsten filament, heated to 2,500 degrees Celsius, undergoes a process of rapid evaporation.
the liberated tungsten atoms travel through the vacuum and deposit themselves on the cooler inner surface of the glass, creating a dark coating that reduces light output and eventually leads to the thinning and snapping of the filament. By introducing argon into the bulb, engineers utilize the gas's relatively high atomic mass, 39.9 atomic mass units, to create a kinetic buffer. The argon atoms act as a dense, invisible crowd. As tungsten atoms attempt to evaporate from the filament, they collide with the heavy argon atoms and are physically deflected back onto the surface of the wire. This process, known as the Langmuir effect, significantly reduces the rate of filament evaporation, allowing the lamp to operate at higher temperatures and for thousands of hours longer than would be possible in a vacuum. Although modern lighting is shifting toward LED technology, the billions of incandescent and halogen lamps still in use globally represent a massive distributed reservoir of captive argon, each one utilizing the gas's inertness to maintain the stability of an artificial sun. In the domain of modern civil engineering and residential architecture, the physical properties of argon are utilized to enhance the energy efficiency of the global built environment through the production of insulated glass units, IGUs, or double-paned windows. The space between the two glass panes in a high-performance window is not filled with air, but with a concentration of argon gas. The logic of this application is found in the kinetic theory of gases. Argon possesses a significantly lower thermal conductivity than the standard mixture of nitrogen and oxygen that constitutes air, approximately 0.016 watts per meter Kelvin for argon versus 0.024 for air. Furthermore, because argon atoms are larger and slower moving than those of nitrogen or oxygen, the process of internal convection, where the gas circulates between the hot and cold panes, is significantly dampened. This reduced mobility and lower conductivity create a superior __55___ slowing the transfer of heat from the interior of a building to the exterior during winter, and vice versa during summer. By utilizing argon as a molecular insulator, modern architecture can achieve significant reductions in the energy required for climate control, effectively using the __56_ gas to mitigate the carbon footprint of human habitation. The preservation of the global food supply and the maintenance of pharmaceutical integrity also rely on the displacement capabilities of argon. In the wine industry, the introduction of oxygen into a bottle marks the beginning of a chemical process known as acetification, where the bacteria Acetobacter aceti convert ethanol into acetic acid, eventually turning a vintage wine into vinegar. To prevent this, winemakers and collectors utilize __57_. Because argon is heavier than air and chemically inert, it can be sprayed into an open bottle or a storage vat, where it settles into a protective layer on the surface of the liquid. This layer is impervious to oxygen, effectively _58, the chemical evolution of the wine. Similar techniques are used in the packaging of high-fat foods and sensitive organic chemicals that are prone to oxidative rancidity or degradation. Argon provides a state of __59_, ensuring that the chemical profile of a substance remains unchanged from the point of production to the point of consumption. The most sophisticated application of argon as a guardian of integrity is observed in the high-tech manufacturing of semiconductors and photovoltaic cells. The production of monocrystalline silicon, the foundational material for every microprocessor on the planet, utilizes the Czochralski process. In this method, a seed crystal of silicon is dipped into a crucible of molten silicon and slowly withdrawn to grow a large, perfect crystal ingot. This process takes place at temperatures of nearly 1,425 degrees Celsius, an environment where any exposure to oxygen or carbon would lead to the formation of defects in the crystal lattice, rendering the resulting chips non-functional.
To maintain the necessary level of purity, the entire furnace is continuously purged with a high-volume flow of ultra-pure argon. The gas serves two critical functions. It prevents the entry of external contaminants, and it carries away the silicon monoxide vapors produced by the reaction between the melt and the quartz crucible. The __60__ of argon is thus the essential condition for the complexity of the digital age. The microscopic precision of the smartphone and the computational power of the supercomputer are direct products of an environment where argon refuses to react with the molten building blocks of technology. In the medical sector, the unique properties of argon are harnessed for surgical precision through a technique known as argon plasma coagulation, APC. This procedure utilizes the fact that argon is easily ionized to form a stable plasma. A high-frequency electrical current is passed through a stream of argon gas, creating a conductive plasma, __61__ that can be used to cauterize tissue and stop bleeding without direct physical contact. Because the argon plasma is non-combustible and the gas itself is inert, the procedure carries a significantly lower risk of tissue charring or accidental ignition compared to traditional electrosurgery. Furthermore, the __62__ nature of the argon plasma allows for very shallow penetration, making it an ideal tool for treating delicate areas such as the lining of the gastrointestinal tract or the surface of the lungs. Here, the non-reactive nature of the gas provides a level of surgical control that ensures the selective destruction of diseased tissue while preserving the underlying healthy structures. Argon also plays a fundamental role in the field of cryosurgery and cryopreservation. In specialized _63_, the gas is subjected to the Joule-Thomson effect, a physical phenomenon where a gas rapidly cools as it expands through a small valve. By precisely controlling the expansion of argon, surgeons can create an __64__ at the tip of the needle, with temperatures as low as -140 degrees Celsius. This localized extreme cold is used to freeze and destroy cancerous tumors, with a level of accuracy that minimizes damage to surrounding organs. The same principle of controlled cooling is applied to the long-term storage of biological samples, where argon-rich environments can be used to supplement liquid nitrogen systems, providing an additional layer of stability for the preservation of reproductive cells and genetic material. The industrial consumption of argon is a testament to its status as the most accessible of the noble gases. Because it constitutes nearly 1% of the atmosphere, argon is produced as a byproduct of the large-scale fractional distillation of liquid air, primarily used to obtain oxygen and nitrogen for the steel and chemical industries. This makes argon the only noble gas that is available in the massive quantities required for heavy industrial processes like __65_AOD in stainless steel production. In this process, argon is injected into molten steel to facilitate the removal of carbon while preventing the oxidation of valuable chromium. This metallurgical fine-tuning is what allows for the creation of the corrosion-resistant steels used in everything from surgical instruments to the structural supports of skyscrapers. Argon is the invisible __66__ that allows for the transition from raw minerals to high-performance materials, serving as a non-reactive catalyst for industrial civilization. The management of argon in these diverse sectors requires a sophisticated understanding of gas dynamics and molecular isolation. In many high-security laboratory environments, argon is used to fill _67_ hermetically sealed containers that allow researchers to manipulate pyrophoric or highly reactive substances, such as alkali metals or certain organometallic catalysts, without risk of fire or contamination.
The argon environment provides a, quote, 68, a volume of space where the chemical laws of the Earth's surface are suspended in favor of absolute stability. This allows for the synthesis of new materials and the study of fundamental chemical processes that would be impossible in a standard atmosphere. The quote, 69, gas is the enabler of scientific risk, providing the non-reactive backdrop against which the most aggressive chemistry can be safely explored. Ultimately, the quote, 70 of argon in our daily lives reveal a material that is characterized by its role as a universal constant. It is the gas that doesn't change, doesn't react, and doesn't interfere. And it is precisely these qualities that make it the ideal medium for the protection of light, heat, history, and technology. We have integrated element 18 into the very fabric of our survival, utilizing its atomic refusal to engage with the world to create a stable foundation for our progress. Every time a high-performance window reflects the heat of the sun, or a specialized weld holds together the frame of a modern aircraft, the invisible presence of argon is performing its duty. It is the guardian of the interface, the material that stands between the intense energy of our machines and the corrosive reality of our atmosphere. The following block will explore the existential finality of argon's story as we track these unchanging atoms into the distant future and consider the ultimate legacy of the gas that refuses to leave a mark. The individual atoms of argon currently circulating within the planetary boundary layer possess a chronological depth that renders the entirety of the biological era a negligible statistical outlier. Unlike the more famous atmospheric gases, oxygen, carbon dioxide, and nitrogen, which are constantly processed, transformed, and recycled through the frantic, energetic machinery of photosynthesis, respiration, and combustion, argon remains in a state of perpetual chemical stasis.
Every atom of argon-40 inhaled during a moment of human respiration has existed in its current monatomic state since it was first vented from the Earth's cooling crust millions or even billions of years ago. It is an element that does not participate in the cycle of life and death. It merely observes it. This total lack of reactivity means that argon does not leave a chemical footprint in the form of oxides or nitrates, yet its very presence constitutes a permanent and unchanging inventory of the Earth's geological history. It is the absolute witness to the planetary narrative, a substance that has remained physically identical while the world around it transitioned from a molten wasteland to a complex biosphere and eventually into a global industrial civilization. In the eventual projection of the Earth's thermal and atmospheric future, argon stands as the most durable constituent of the terrestrial environment. As the Sun continues its stellar evolution, its increasing luminosity will eventually trigger a runaway greenhouse effect on Earth, leading to the evaporation of the oceans and the subsequent breakdown of the carbon silicate cycle. During this transition, the oxygen produced by the biosphere will vanish as life reaches its terminal limits, and the nitrogen may eventually be sequestered or lost to space. However, the argon will remain. Because it is chemically inert and relatively heavy, it is less susceptible to atmospheric escape than lighter gases like hydrogen or helium. Trillions of years from now, long after the last biological organism has succumbed to the increasing solar radiation, the 0.93% of argon will still be present in the thinning atmosphere, a silent and invisible monument to a planet that once possessed the internal heat to produce it and the gravity to hold it. It is the final punctuation mark in the story of the atmosphere, the material that remains when all the reactive components have been exhausted or stripped away. The existential significance of argon is further illuminated by its role in the deep time of the radioactive battery. The continuous production of argon-40 from the decay of potassium-40 is a finite process. Eventually, the Earth's internal reservoir of unstable potassium will be depleted, and the breathing of the crust will cease. This marks the transition from a geologically active world
to a dead world, similar to the current state of the Moon or Mercury. The total volume of argon currently found in the atmosphere is thus a physical measurement of the Earth's total energetic expenditure. It is a record of every volcanic eruption, every tectonic shift, and every hydrothermal venting that has occurred since the Hadean Eon. We are currently living in a specific window of time where the accumulation of argon has reached its peak, providing a dense, non-reactive buffer that stabilizes the pressure of our environment. To understand argon is to understand the ticking clock of the planet's internal fire, a fire that is slowly fading toward a cold, leaden equilibrium. The monatomic nature of argon, the fact that it exists as individual atoms rather than molecules, is a mathematical proof of its isolation. According to the kinetic theory of gases, the specific heat ratio of 1.67 for argon is a direct reflection of its 3 degrees of freedom. Unlike diatomic nitrogen or oxygen, which can store energy through rotation and vibration, an argon atom can only store energy through translational motion. It is a billiard ball in a world of complex, vibrating structures. This simplicity is its greatest strength. There are no bonds to break, no configurations to alter, and no chemical vulnerabilities to exploit. This is why argon is the ultimate guardian of human records and technological integrity. It does not possess the capacity to change, and therefore it prevents change in everything it surrounds. The laziness that was once a source of scientific confusion is now recognized as a state of perfect thermodynamic rest, a destination toward which all matter eventually trends. In the far future, should an extraterrestrial intelligence or a successor species attempt to reconstruct the history of the Earth, the isotopic ratio of argon will be their primary data source. The relative abundance of argon-40 compared to argon-36 and argon-38 will provide an immediate and uncompromising measure of the planet's geological age and the extent of its crustal degassing. Argon acts as a universal language of planetary maturity, an atmospheric signature that reveals the internal complexity of a world without the need for physical sampling of its interior. It is a material that transcends the limitations of culture, language, and biological perception, offering an objective, mathematical record of a world's existence. The argon atoms currently filling the rooms of our homes and the labs of our scientists are the same atoms that will be used to judge our planet's history in the distant reaches of the future. The legacy of argon also includes its role as a silent partner in the storage of the most dangerous materials produced by human civilization. In the deep geological repositories designed for the sequestration of high-level nuclear waste, such as the Onkalo facility in Finland, the surrounding environment must remain stable for hundreds of thousands of years. While the primary barriers are composed of copper and bentonite clay, the presence of noble gases like argon within the subterranean pore spaces provides a non-reactive medium that does not facilitate the corrosion of storage canisters. Argon is the environment of no consequence, the substance that ensures that the intense radiation and heat of the waste do not trigger unwanted chemical feedback loops with the surrounding rock. It is the final layer of safety, a gas that provides protection through its refusal to act, acting as a molecular padding that isolates the legacy of the atomic age from the biosphere. When considering the ultimate fate of the universe, the story of argon enters the realm of the heat death, or the Big Freeze. Trillions of years into the future, when the last stars have burned out and the galaxies have drifted beyond each other's horizons, the individual atoms of argon will still persist. Unless protons themselves eventually decay, a process predicted by some theories of physics but yet to be observed, the argon nucleus will remain as a stable, tightly bound collection of 18 protons and 22 neutrons. In a universe where all complex structures have disintegrated and all energy has been dissipated, these monatomic, noble survivors will be among the last coherent entities in the void. They will be individual, indestructible bullets of matter, drifting through an infinite darkness, carrying the memory of the silicon-burning phase of a long dead star and the radioactive decay of a long frozen planet. Argon is not merely a constituent of the air, it is a fundamental unit of cosmic permanence. The transition from the frantic reactivity of life to the noble stability of argon represents the ultimate lesson of the elements. We are a species defined by our interactions, our bonds, and our constant exchange of energy. We are reactive in every sense of the word. Argon, by contrast, demonstrates the power of the inert. It teaches that there is a profound utility in being unchanging and a critical value in being unreactive. The invisible guardian does not seek to dominate the atmosphere or participate in the biological struggle. It simply remains as a constant, reliable presence that provides the pressure and the protection necessary for everything else to exist.
It is the lazy element that does the most work by doing nothing at all. A paradox of physics that has allowed us to build the tools of the modern age and preserve the records of our past. As the narrative of element 18 concludes, the focus returns to the simple act of breathing. With every inhalation, the human body is taking in a trillion-ton legacy of geological time and cosmic synthesis. The argon atoms are there, silent and indifferent, moving through the lungs and back into the room without leaving a trace. They are the same atoms that witnessed the cooling of the first oceans, and the same atoms that will witness the final expansion of the sun. We are merely temporary vessels for this ancient gas, brief participants in its multi-billion-year journey from the crust to the void. The 1% of the air that we once ignored is the most stable thing we have ever touched. A material that reminds us that in a universe of constant change, the most noble path is often the one of absolute, unchanging stability. The final image of argon is one of total objective transparency. It is the gas that reflects nothing, reacts with nothing, and asks for nothing. It remains perfectly clear and perfectly stable, encircling the Earth in an invisible embrace that has outlasted every empire and will outlast every star. It is the silent chronicler of the world, a material that carries the history of the elements into a future where the word history may no longer have a meaning. Argon is the eternal witness, the non-reactive anchor of a changing world, and the silent guardian of the human experiment. Its peace is the peace of the filled electron shell, a state of atomic perfection that requires no external validation and fears no environmental decay. In the end, there is only the argon, clear, cold, and noble, drifting through the ruins of time as the last, best evidence that a planet called Earth once existed in the light of a star.